Well, with no path and no circuit, I wonder what patterns we can find. This one has a degree of 1, that has a degree of 1, a degree of 1, a degree of 1, and a degree of 4. Well, let's look at that. Okay. If we have a lot of 3's, let's back up and feed another idea that we talked about. If we have a lot of 3's, then the answer is a no. Well, it's not about the 3's. It's about the odds and the evens. That's really it. It all goes down to the odds and the evens. So let's talk about an Euler path exists. An Euler path exists if exactly 2 vertices have a degree, well, that, having a hard time writing here, that is odd. Or, okay, we're going to leave you hanging on that one for a second. We'll finish that sentence in just a moment. But in the meantime, what we are going to do, excuse me, move that out of the way a little bit. Yep, sliding this over, there we go. Sorry, trying to get some other stuff out of the camera angle. There we go. Didn't work, but whatever. An Euler circuit exists if, okay, let's look at some of the ones that did exist. That one was a yes. Look, they're all even. This one was a no, that one was a no. I'm flipping through my notes. That one was a yes and a yes. Oh, they're all even. That one was a yes. They're all even. So here we go. I know I'm flipping through. I know I'm all over the place. Trust me, I'm going somewhere with this. Didn't get the camera adjusted like I wanted a minute ago, but that's okay. Euler circuit exists if all vertices, all the vertexes, that's plural for vertex, is vertices, all vertices have an even degree. Okay, an Euler circuit exists if all the vertices have an even degree. If exactly 2 vertices have a degree that is odd, it's an Euler path. But also, a circuit is a path. So again, let's grab Post-it notes and let's talk about this really quickly. If I was to just throw down an A and a B and a C and a D and just connect them in sort of a square here, and I'm going to just say, oh, the degree of this vertex is 2, and that one's 2, and that one's 2, and that one's 2, then, well, we have a path, and the path goes A to B to C to D back to A, but that's also the circuit, because we started here and ended here. So path is the circuit. So a path exists if 2 vertices have a degree that's odd, or all vertices have an even degree, which really means that you have an Euler circuit, because a circuit is a path. All right, let's slide down here, and here's where the stuff gets really practical. You're going to deliver mail, and when you do, you're going to have your route highlighted by each of the pictures below. For each, state if an Euler path exists and if an Euler circuit exists. Okay, well, here's your picture. And in our picture, and you don't have to write what I'm writing, but I'm going to white out some stuff here. We're going to put some numbers in the appropriate place over each vertex. Now, why did I do that one? I don't even know. Here we go. So here goes. This vertex has a degree of 2. This vertex has a degree of 2. So coming out of here, there's 2. This one's 3, this one's 3, this one's 2, this one's 2. All right. I'll look at this, and I'm looking sliding up here, and I'm saying, well, does an Euler circuit exist? Let's go here. Well, no, I have some odd ones. So no Euler circuit. And I think it's worth saying why. No Euler circuit exists. Let's capitalize the beginning of that sentence. Because 2 vertices have an odd degree. So no circuit, which means I can't start and end in the same place. No matter how hard you try, you'll never start and end in the same place and cross all the edges. Like we can go around, but then you never got this one in the middle, right? However, that's an awkward W, isn't it? An Euler path, I will abbreviate, exists And although I'm not going to label these as A, B, C, D, and E, I think we could just kind of trace through it. And let me give you a hint. If you're ever going to find an Euler path, start with an odd vertex. I think that's worth writing down. I'll write it down in a second. But if you need to find an Euler path, you start with an odd vertex. There is no way you will get the path with this one, this one, this one, or this one. So let me prove it. Let me try. Not a proof, but a try. So one, na, but never got the one in the middle. Na. Never got some of these up here. Na. Never got that one. So no, it's not going to work. But if you start here, you can go da, 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 and it was a path because you started here, you ended here. Didn't end in the same. You started in one place, ended in another, which means it's a path. However, if you would have started and ended in the same place, it's a circuit, and technically it's a path also. All right, but da, 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 da. There we go. We started and ended at odd vertices. We'll write down the importance of that in a minute. So here goes. Let's try another one. Vertex here, 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 here. Let's not white those out. That's just awkward. Degree is 2. Degree is 3, right? Okay, so like 1, 2, 3. Degree is 3. The degree is 1, 2, 3 here. The degree is 2 here. 1, 2, 3, 4 here, 3 here, and 2 here. Okay. I have 1, 2, 3, 4 that have an odd degree. Obviously, the circuit is out, but exactly 2 vertices have a degree that is odd. No, I have more than 2. I don't have exactly 2, so no Euler paths or Euler circuit exists because, I'm abbreviating a lot, there are 4 vertices with an odd degree. Okay, we have a little space at the bottom of the page to write down the important stuff that I mentioned a minute ago, so let's do it, and here it is. When finding an Euler path, I'm going to highlight this in a minute, it's that important. Always begin with a vertex that has an odd degree. We talked about this just a minute ago, but I think it's worth writing. So again, if I want to, running out of ink in my highlighter, it's tragic. Running out of highlighter fluid. So if I wanted to find an Euler path and I knew I could find one, then I would need to start with an odd degree. So I just wanted to take that space and write it. We have 3 more. Let's go through them. And when we do, I think we can use a little white out here. I think in the future I'll probably leave some blank space in these. There we go. I'm just taking this opportunity to do this right here just for the sake of being able to see things easily. Sorry to waste your time in this video. There we go. Okay, we're gonna just state the degree. Oh no, I dropped my pen. Looks like I'll have to switch pens. It's all right. The degree is 2. The degree is 3. The degree is 3. The degree is 2. Okay, all right, already. I have 2 of them with a degree of 3. If I have any more, this thing's off. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 2, 3. See? No Euler path or Euler circuit exists because there are 1, 2, 3, 4. 4 vertices. Same reason as the last one. With an odd degree. Okay, next one. 2, 4, 3, 2, 2, 3. Okay, we've already reached our limit. If we go over that, can't have it. Now, if we had a vertex that had an odd degree and only one vertex, it would still be a no. 4, 2, 2, 1, 2, 3, 4. Ooh, 4. There we go. Euler path, yes or no? Think so. We have 2 of them. Exists because there are exactly, how do we turn that into an E? Exactly, there we go. Let's get ahead of myself. Exactly 2 vertices with an odd degree. There is no Euler circuit. All right, let's slide up and do this one. 2, 3, 2, 4, 2, 2, 3. We already have a couple odds. 4, 4, 4, 2. Yes, look, 2 odds. Therefore, we have an Euler path, but no Euler circuit. I don't feel like writing this again. All this is the same answer as this one right here. Exactly 2 odds.